Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to continue with Castigliano's theorem in finding deflections in beams. We did it last session with trusses, and we found vertical deflection at a point, at a joint in a truss. And the truss, if you remember, that joint was not loaded, so we had to add a fictitious load. And after we did our work, remember the deflection was the partial derivative of the strain energy with respect to the force. So in the case of axial loads, which is a truss, it would be FL over EA times the derivative of F with respect to P. In cases where you have the loads are not along the axis of the beam, meaning we have moments. We have moments and shears, but the shear usually is negligible. So the equation that we will be using to find delta or the deflection at a point, remember that there we said FL over EA. When it, in the case of a moment, it becomes ML, which is the length, over EI. So I'm going to take 1 over EI. But then because the moment changes from a point to point, I really need to take the integral from 0 to L dx, and then multiply like we did there. We multiplied with the partial derivative of F with respect to P. Here it would be M with respect to P. That's it. In this problem, I want you to find the vertical deflection at point C, the midway, the midspan of the beam that is really long, okay? So in that case, we have to find an equation for the moment at every section. Well, notice that from A to C, nothing changes. It's just the distributed load. So I will have to find an equation for the moment at any point between 0 and 5. But after the concentrated load, things become very, not confusing, but complicated. So I have a reaction, I have a distributed load, I have a concentrated load. It's a lot of work. Luckily, I can start from B. And in that case, I don't have anything between B and C except the reaction. Much easier, right? So, but before we do anything, and notice we want the deflection at C, and C has a concentrated load, so I don't need a fictitious load. I'm simply going to call that P. Why? Because when I get the partial M, partial P, I can take it if it's a P, right? But if it's a number like 20, how can I take the derivative like I said last time? So basically what we have here, we can quickly find the reactions. I know the 20 or the P would become P over 2 and P over 2, and then I can ignore them. Say, how can I ignore it? Well, because instead of P, if you draw this as P over 2 and P over 2, this one produces a couple, no forces, just a pure moment going clockwise, and this with the other half will do counterclockwise couple. These couples cancel each other, so you can just ignore them when you take the reaction. If you don't believe me, you can use P over 2 and P, but it really doesn't matter. Meaning, when I take the moment to find the reactions AY and BY, so again, I'm going to say this is 5 meters, this is 5 meters, this is my X, this is my Y. And here, for the sake of finding reactions, I simply can replace this. 4 times 5 is 20 at the distance of 2.5. So I can say 20 kilonewton, and that distance is 2.5. Not to find moments, of course, but to find reactions, it's faster. It's the same thing, right? So we start by taking sum of the moments about B equals 0. This is A, this is B. counterclockwise is positive. So I only have to worry about these two, right? I have AY here. I'm not going to say AY because I need to find it, but it's going clockwise. So negative 10 AY plus 20 times 7.5 equals 0. You say, where is P over 2 and P? I told you, ignore them. If you don't want to, just add two terms and see what you get at the end. If it's different from what I get, just drop me a line and say, oh, you messed up. It should be this and that. Okay, I divide by 10, move AY to the other side. 2 times 7.5 is 15. So AY equals 15 kilonewton, positive meaning going up. So I'm going to say here 15 plus. When I go to the right-hand side, I can say sum of the forces in the Y equals 0, up is positive. I have, again, I'm not going to worry about the P's, okay? I'm going to say 15 going up, minus 20 going down, plus BY equals 0. 15 minus 20 is negative 5, move it to the other side. BY equals 5 kilonewton, positive meaning it's up. So that's plus 5. I found them. So next we need an expression for the moment to the left of P and to the right of P. Let's call them M1 and M2. So if this point is A, I have a reaction going up. I have a moment from, so if that distance is x1, any point here, any point, I can call it x1, then the reaction, then first of all, this is 15 plus P over 2. And like we said, for the moment, you're going to say that for x1, and that distance is x1 over 2. And finally, you have a moment, let's call it m1. So to write an equation for the moment at A, we're going to say m1 is going counterclockwise. So instead of saying plus and minus, I'm going to say equal. And then anything going negative, I'm going to write it positive because I moved it to the other side. Basically, I would say m1 minus this times x1 plus this times x1 over 2 equals 0. And then I'm going to move them anyway. So that becomes 15 plus P over 2 times x1 minus 4x1 times x1 over 2 is 2x1 squared. That's the moment m1 at any section at a distance of x1. But then remember, I need the partial m1 by partial p. I have p over 2 times x1. That's the only term that has p. So when I take the derivative with respect to p, I get x1 over 2. So the first half of the integration, let me write it down here. The integral, first of all, 1 over ei, integral from 0 to 5. I'm going to multiply these two together. But now, since I already took the partial derivative, there is no reason to use p. Just call it 20. 20 over 10 is 20 over 2 is 10 plus 15 is 25. Multiply that by x1 over 2, so it's 25 over 2 x1 squared. And then you multiply these two, the 2 and the 2 cancel, and you get minus x1 cubed dx1. That's the deflection of this part. But still, there is another deflection from the right. So on the right-hand side, I have 5 plus P over 2. And then at the distance of x2, the moment would be a negative moment. So it doesn't matter. This is negative, this is positive. So I can say m2 equals 5 plus p over 2 times x2. Partial m2 by partial p is x2 over 2. So now I'm going to add 1 over ei. I'm starting at b, so the integration is also from 0 to 5. But now it's just this times that. Okay? So I have p over 2 is 10 plus 5 is 15 over 2, 15 halves, x2 square dx2. I'm done with the math. The rest is easy. So I will have 1 over ei times, can take this integral, x2, x1 square is x1 cube over 3. So that would become 25 over 6 x1 cube minus x1 to the 4 over 4. And that's evaluated from 0 to 5. And that's also evaluated from 0 to 5. So I just can add them up. This would be 5 halves because 15 x cubed over 3. 15 over 3 is 5. Get 5 halves x2 cubed. And all of that evaluated from 0 to 5. Of course, at 0, you get 0, so you don't have to worry about that. You get 1 over ei. Okay, let's do the math. So I have 5 cubed is 125 times 25 over 6 minus 25 squared is 625 over 4 plus this would be also 625 because 5 times 5 times 5 times 5. So plus 625 over 2 equals. Did we do the math correct? I don't know. I have to check the numbers. Over ei. Okay, quickly. We said this is 15, that's 5, that's sure, correct. And this is 10, so 25 over 2 x1 square. And 2 over 2 is 1, so x1 cubed. And this would be 15 x2 times x2 over 2, so 15. Okay, 15, so that would be 5 halves x2 cubed. That would be x, this would be cubed over 3, which make it 6. 125 times 25 over 6 minus 625 over 4 plus 625 again over 2. Okay, so meaning you add 620. Okay, so now notice the moment is kilonewton meter, and then we multiply by, so this is kilonewton meter, and this is meter. So when you multiply them, the numerator is kilonewton meter square. The denominator, so we can say 677.08 divided by 200 times 1600 times 10 to the 6. Now, this is in megapascal. So we're going to multiply by 10 to the 9 to make it in Pascal. Pascal is Newton per square meter. We don't want square meter. We want square millimeter, right? Okay. So, these are per square meter. So you divide by 10 to the 6. In the numerator, I have kilonewton, so I would multiply by 10 to the third to be Newton like that and cancel each other. And then I have meter square, so times 10 to the 6. Okay? Notice that this over that is 10 to the third times that is 10 to the 9th, and this is 10 to the 9th. So everything now, that would be in meter, right? Because even though we did multiply here to make that millimeter square. And this, we made it millimeter square. Yeah, I think that's correct. So you have to multiply by 1,000 again to make it in millimeter. This is gigapascal, meaning, or after we multiplied it by 10 to the 9, it became Newton per square meter, right? So we had to multiply by 10 to the 6 to make it per millimeter. That's so when you multiply that by 1,000 and then you divide by 200 by 1,600, you get 2.11 or 12 millimeters. I have to check the numbers. For some reason, I think, yeah, it should be correct. Okay, if you find any error, you can drop me a line. We can review it again, but I will review it. If I find something, I will post it. Thank you very much for your time. Hope to see you soon. Have a nice day. Bye.